Hello everyone. Today in this video lecture we'll be learning about receiver design, then responsivity and what are the noises in a detector. Okay, first we'll deal with receiver design. The receiver has certain blocks that are inbuilt in it. Okay, so we classify the different section in the receiver, optical receiver, as the front end, the linear channel and the decision circuit. As you can see from the figure, the first is front end, in the middle comes the linear channel, and the last part of the receiver design is the decision circuit. So, uh, coming in detail about each of the part, the front end contains the photo detector and the preamplifier. As we have already discussed, the main function of the photo detector is to convert the optical signal to the light electric signal, and the voltage supply in the front end here gives the necessary bias that is required for the operation of photodiode. As we all know, if we are using pin photodiode and avalanche photodiode, we are always working in the reverse bias condition. So this reverse bias will be provided by the voltage supply. So for the transmission of the signal, and we require certain preamplification, and that preamplification, so as it is not affected by noise, it is done by the preamplifier. And the next is the linear channel. The linear channel has amplifier and automatic gain control and the filter. So the function of the amplifier is to further boost the signal, and automatic gain control, as you all learned in the analog communication, it is a continuous feedback system which controls the gain of the system depending upon the input. Okay, so it is a feedback loop. So filter does the filtering process, like only the allowed signal is being passed and all the unwanted signals and noises are being filtered out. So decision circuit and clock recovery, this comes the decoding part. Every signal must be decoded. The signal will be sent with some coding from the transmitter side, and the decoding is done by the decoding is done from the decision circuit. Okay. So the next topic is detector responsivity. So as we all know, we have a semiconductors lab on which our incident photon of particle energy h nu is incident, and if this energy h nu is greater than the band gap energy, the electron hole pair is generated. The electrons get excited to the higher level, leaving behind the hole in the lower level. As a result, electron hole pair is generated. More the incident photon, more the electron hole pair is generated. Because of this electron hole pair being generated, an electric field is set up, and if you apply a voltage, a current will flow, and this current is given by photocurrent, denoted by photocurrent IP. So the incident current is IP, and the incident optical power is denoted by PN. As you can see from the figure, there is a semiconductor lab which is being used as a photo detector. There is an incident light of energy h nu that is being falling on the semiconductor. Because of it, electron holes are generated. An electric field is developed. When we connect a potential voltage drop, the current IP flows, and the current IP is given by R into P in, where R is the responsivity of the photodetector and the unit of R is amps per watt. And the responsivity can also be expressed in a fundamental quantity eta called the quantum efficiency. The quantum efficiency eta is denoted by electron generation rate by photon incident rate. Nothing but output by input. Our output is electron generation, and our input is photon incident rate. So the electron generation rate is given by IP by Q, where IP is the photocurrent and Q is the charge of the electron, divided by incident photon rate, P in incident power, divided by h nu energy. So it can be rewritten as h nu by Q into R. By using the equation, R is equal to IP by Pn, and the responsivity R is given by eta Q by HV, and it can also be written as n lambda by 1.24, where we are substituting the value for charge of the electron and Planck's constant, and we are giving and we are substituting the value of for Vs, the velocity of light in free space. Then we get the expression for R is n lambda by 1.24. So the responsivity of a photo detector from the expression we can see it increases with the wavelength. Simply because more the wavelength, more the photons are incident, more the electric current. The photocurrent IP is being produced. So there is a linear dependence of lambda and lambda, and with the generation of electrons. And this happens, generation of electrons and whole pair generation happens only when the incident photon has an energy greater than the band gap. The band gap is denoted by Eg. And so when the condition that it should not should be always not the condition that the incident photon has energy greater than the band gap. So the cases where the incident energy doesn't have the energy greater than the band gap energy, then there is no electron hole generation. There is the current, the photocurrent is also negligible. As a result, the quantum efficiency drops to zero. So in this slide, you can see the comparison of performance. Here, the generating operating parameters of a silicon germanium gallium arsenide pin photodiodes, as well as for silicon germanium gallium arsenide avalanche photodiodes are being tabulated. So the various parameter, wavelength, responsivity, dark current, rise time, bandwidth, bias voltage, for each of the factors, their units, their values, are noted for both the pin and avalanche photodiodes. This is just quick comparison between the various diodes. So next topic is the noise in detectors. The noise is present in almost all communication system. The noise can be described as an unwanted component of signal that is present in a communication system that disturb the transmission and reception of the signal. So it is present in almost every communication system. So in fiber optic communication system, the photodiode must detect a very weak optical signals. That is, the optical communication system must distinguish between the very weak signal and the noise that is present in the communication system. So the one of the important property of an optical communication system is that all the photodiodes and its associated electronic amplification circuitry should be optimized to that specific signal to noise ratio. So there is a specific signal to noise ratio that is being maintained so that easy detection of the signal and amplification is possible. So the next is signal to noise ratio. Signal to noise ratio can be defined as signal power from photocurrent divided by photodetector noise power plus amplified noise power. So for better signal noise to ratio, we should have a high photocurrent. For high photocurrent means high quantum efficiency, and for better SNR or signal to noise ratio, we should be having a lower denominator. Lower denominator means photodetector noise power, and the amplified noise power should be kept low as possible.